All right, let's start talking about double integration with polar coordinates. Before I do that, let's go ahead and talk about something. I probably should have talked about this before when we're talking about double integrals using Cartesian coordinates, okay, x and y. A type 1 region of the xy plane is a region bounded by two vertical lines and two functions of x, okay, like we see here, okay? And in this particular case, we've got the vertical lines being x equals a and x equals b. We've got a function of x that lies above another function of x here. This is called, in this particular case, y equals h of x, and the lower one is y equals g of x. And you can see this forms a certain region of the xy plane here. We call this a type 1 region. This is easy to integrate in the y direction first and then the x direction second. Okay, so in this particular case, if you look at this, the actual integral here, if I was to integrate over this, some continuous function of x and y, you'd want to integrate in the y direction first and then in the x direction, right? The integral would look like this. You'd be integrating dy dx. Y goes from g of x up to h of x, okay? And then, of course, constants of limits of integration on the outside there. X is going from a to b, okay? That would be what we would call a type 1 region. Now, a type 2 region is backwards to this. You've got what? You've got two horizontal lines, and then you've got what? X is a function of y, and two different cases here. X is a lower function of y, x equals g of y, and an upper one, x equals h of y. You guys can see here, if I want to integrate some continuous function over this region, what I would like to do is what? Integrate in the x direction first, and then in the y direction. You can see here, same as the other case, would you really want to go in the x direction first? Oh my goodness, that would be a mess, wouldn't it? Oh, you'd have to break it up into multiple integrals. Same thing here, you know. So this one looks like this. The integral of f of xy dx, you want to come this direction first. So x is going from g of y up to h of y. So that inner integral just being some function of y in the end. And then you're integrating that function of y dy. Y goes from c to d. Okay? Now we'll have similar ideas here occurring when we're talking about integrating with polar coordinates. All right, and if you remember polar coordinates from Calculus 2, every point in the plane can be characterized by what? Two coordinates, r and theta, where r is the distance from the origin, and theta is the angle measured from the positive x-axis to the ray emanating from the origin and terminating in the point itself. R and theta, if you remember, are not unique. You could have negative values for r, and theta could be what? You could add multiples of integral multiples of 2 pi to this as well. But we're not going to be going in depth into graphing polar functions, but we want to be aware of graphing a few of them, okay? You can go ahead and review your Calc 2 on that if you need to. One thing we do have to remember is some of our basic trigonometry. Do you remember this from Calc 1? X equals r cosine theta, y equals r sine theta. This allows a conversion from polar coordinates into the Cartesian. All right? All right. Let's take a look at something here. This is just a regular rectangle in Cartesian coordinates, right? It's bounded by two vertical lines here, x equals a, x equals b, and bounded by two other lines, these being horizontal, y equals constant c, y equals the constant d, and you get a regular, what we call a rectangle. Now, something we call a polar rectangle, and other people will just call a circular sector, is the following. We've got a ray emanating from the origin here, theta equals alpha. And then we've got a second one, theta equals beta. Okay. And then we've got r equals a and r equals b. You know those would end up being circles centered at the origin with radii a and b respectively. The region bounded by these curves in the xy plane gives what some people will call in trigonometry circular sector, or geometry, if you remember that. We will also call it a quote-unquote polar rectangle. Okay? A polar rectangle. And we'll see why that's really good terminology later on when we start talking about transformations at the end of the chapter here. Okay? Now, you guys remember, again, from Calculus 2, that what you typically would have in polar coordinates when you're graphing, r is a function of theta. R is a function of theta, and that's what we're going to be doing throughout. Okay, so in this particular picture, I've got r is some funky function of theta here. So every value of theta yields a particular distance from the origin there. Okay, and this would be what? And I might think about maybe this would make a region of the xy plane. Okay, region of the xy plane. But I'm going to be thinking in terms of polar coordinates here. Now, I might want to integrate over that region. Okay, want to integrate over the region. Now, if you go back and think about what we did with double integrals in terms of Cartesian coordinates, what did we do? We took the whatever region you were dealing with and did what? We divided it up with what? Sub-rectangles, right? So we think about dividing it up into things that look like this, right? Boundaries are vertical lines and horizontal lines, right? We're going to do something similar here, but we're thinking in terms of polar coordinates. So we're going to have what little subpolar rectangles here. So we're going to have what theta, fixed values of theta here, cutting it with these rays, and then what? Fixed values of r. Okay. And we're going to imagine dicing up or partitioning up a region like this in terms of those polar subrectangles. Okay. And there's a particular one here. You can see this is, imagine this being blown up here. And the next thing we're going to talk about is actually finding the area of one of these polar rectangles. So how do you find the area of a polar rectangle here? Okay, how do you actually do that? Oh, it's not hard. Let's think about doing this one. Okay, we just need a little geometry. Let's try it here. What's the area of a polar rectangle? Should be fairly easy. Let's go back and just assume I'm trying to find the area of that. Okay? Let's see, what were the limits here? I was going theta goes from alpha to beta. R goes from A to B. Okay? I might change my designation to that stuff later, but let's go ahead and see what happens here. Okay? The way I'm going to end up doing it is the following. Let's just talk about the area of part of a circle first. Okay? Area of part of a circle. Okay, let's say this is what? Theta equals alpha. Theta equals beta. Okay? And let's say the radius here is b, the larger radius. Okay, this is x and y. All right, let's talk about finding the area of this thing here. That whole pie slice. Well, it's actually going to be pretty easy. What you're going to do is take the area of the whole circle. All right, this is supposed to be a circle here. The area here would be, what's the area of a circle of radius b? It would be pi times b squared. Okay? And then what I'm going to do is think about, in terms of a whole circle, theta is actually what? 2 pi radians. There's 2 pi radians to go all the way around a circle, right? Okay? Now, the angle represented here between these two is actually just the difference of the angles. So it looks like the area of that pi slice should be what? Pi b squared times this fraction, beta minus alpha over 2 pi. And when we simplify that, it looks like what? The pi's cancel. Okay? So we've got 1/2 b squared beta minus alpha. Okay. Alrighty. Now, what about the case where we've got this region bounded between two different radii, r equals a, r equals b? Again, I still have these same two angles. Theta equals beta and theta equals alpha. What would be the area of this bit? Okay. Well, it's going to be very simple here. I'm going to imagine finding the area of this whole pi slice here. Okay. And then what? The area of this whole pi slice there, and subtract the two. And what I should have remaining should be area of that little polar rectangle. So the area here would be, let's see, 1/2 the big pi slice, PIE, not PI, right? All right. And there's the area of the smaller pi slice there. That would be a squared beta minus alpha. So this would end up being 1/2 b squared minus a squared times beta minus alpha. Okay, so this is for the polar rectangle area. And we're going to end up with this. Okay, now we're going to be rewriting this. We'll be writing this in a slightly different fashion here. Okay, let's go ahead and rewrite this just a little bit here. Okay, so but some basic geometry. Okay. All right, just change some of my notations a little bit here. Okay, so let's say I have this being my original R. I could call it R1 or just call it R, I don't care. Okay. And let's say this is, so this is R equals R1. This is R equals R1 plus some change in R. Okay. And then this is going to be theta equals theta 1. And this one will be theta equals theta 1 plus a change in theta. So I'll call that delta theta. Okay? Alrighty. And then I want to express this area again. So let me shade this again. Okay? I'm still going after that. I'm just going to use a new notation here. Well, the area of my polar rectangle would be 1/2 the larger radius squared minus the smaller radius squared times beta minus alpha. That means this angle minus this angle. Let's just do that one in our heads. That's the change in the angle, right? That's what I'll call delta theta. Now let's go ahead and expand this just a little bit. It's R1 squared plus 2 R1 delta R plus delta R squared times delta theta. Okay. All right, the R1 squareds drop out. And then I've got half of this guy, so that's R1 delta R delta theta. Okay. And then for the rest of it, I've got what? 1/2 delta R squared delta theta. So this would be the area that I'm looking for. Maybe I should give this a name. Okay. All right. Later on, I should really call this, we're going to be dividing these things up like I had in this picture. So maybe I'll even call this something else. I'll call it change in area, delta area. okay, with all those changes going on. All right, but this is going to be our idea here. And what we'll often do here is just go ahead and, suppress the subscript. It'll be some value of r. This is something we want to remember here as we go through our calculations here involving double integrals in terms of polar coordinates. Now next I'm going to go ahead and put up a little slideshow. Okay, let's go ahead and go to our slideshow PowerPoint presentation here. This is from OpenStax. As you can see, I will be posting this online. All right, the first thing here, OpenStax is talking about the type 1 and type 2 region. Okay, we've already discussed this, but there you get a good gander at it. Okay, let's go to the next slide here. Sorry. Okay, there's type 2 region. Okay, or regions. There's a region D that can be described as either a type 1 or type 2. It's really both. Okay, most regions are neither, unfortunately, but we can actually break them up into a type 1 or type 2. Okay, that's done there. All right, so you can contemplate that. That's not really what I want to focus on now, but just for the sake of completeness. Okay, let's go ahead and go to what we were talking about involving polar coordinates. Okay, I'm going to start out with a polar rectangle. Okay, you can see that the big colored one right here. Okay, you guys remember when we started out with our original double integrations, we went ahead and integrated over regular rectangles in Cartesian coordinates. It's the easiest thing to start with. But here's the idea. So I've got a polar rectangle, and I'm going to go ahead and partition it up into a bunch of smaller sub-polar rectangles. I'll just call them sub-rectangles. Okay? And when you do that, okay, you can imagine having done that, and then I'll take a sample point in each of those sub-rectangles here. Okay? A sample point in each of those sub-rectangles. Okay. Now we're going to sit here and talk about the actual area of each of these sub-rectangles here. OpenStax does it slightly differently from what I ended up doing right here. They talk about the average radius here. Okay? Which is a good way to do it. That's another way to think of it. Okay, but this is the idea behind using polar coordinates to actually integrate a continuous function of x and y over a region like that. Okay, now the regions we will be integrating, however, of course, are more general than just these ideal polar rectangles. Okay, we'll keep this in mind. Let's go to the next slide. Okay, finding the volume of a thin box above a polar rectangle, cap r sub ij. Okay, so we've got our sample point down here. Okay, we've got polar coordinates for that sample point. And then the function is a function of x and y typically, but we can change it into what? A function of r and theta, because we remember that what? X equals r cosine theta, y equals r sine theta. So it really becomes a function of r and theta if we would like it to. Okay. Now, just to show you, here's some regions. If you're going to go, say, if you're dealing with a situation here, you want to use polar coordinates, you want to do it in situations where it's really an advantage. Now, if I'm integrating creating a double integral over a region like this right here, a semicircular annulus, this is begging for what? Polar coordinates, right? You want to choose it in such a way what coordinate system you're going to use based upon the ease of actually setting up the integral. Okay, so that means really it's the region over which you're going to be integrating that will be typically deciding which type of coordinate system you want to end up using. Okay, this is begging for it here. There's another region where top half of a cardioid, remember r equals 1 plus cosine theta, for example, that would be a cardioid. That would be perfect for polar coordinates if we were integrating some function of x and y over that region they're calling D. Okay. Now, what are our more general situations here? They're calling it D this time here. For an easy situation, so this is kind of like what would be with a type 1 integral for polar coordinates, where what? The boundaries are what? Two rays, theta equals alpha, theta equals beta, and then what r is bounded between two functions of theta. So this is kind of like a type 1 region for polar coordinates, okay? By the way, there's not going to usually be a type 2 regions for polar coordinates, because usually we do what? We go r is a function of theta, right? Not vice versa. Okay, but if you look at this thing here, so our general polar region, it's bounded by these things. Okay, let's see, this is what? R is h sub 2 of theta, and this other one is r is h1 of theta here. Okay, so polar region, alphas or theta is between alpha and beta, r is between h sub 1 of theta and h sub 2 of theta. If I was going to integrate some function of x, y over that region, I would be integrating from what? Theta goes from, that's my outer integral, right? Theta goes from alpha to beta. R here goes from what? H1 to H2. And then I've got f of x, but that's r cosine theta, y, so that's r sine theta. Now don't forget here, now I'm going to show this in greater depth here, but don't forget when you're using a polar integration, there's going to be this little factor r in there. It's not just dr d theta, okay? It's going to have r dr d theta, and we'll show in greater depth in a minute here why that is so. Okay?